Everyone, and today I will present our latest work entitled Joining CNNs and Transformer Networks for Enhanced Breast Ultrasound Image Segmentation, done by me, Jaouad Tagnamas, and my professors Hiba Ramadan, Ali Yahyaouy, and Hamid Tairi, as part of our participation in the ISCV conference. So let's start by an outline, which I will be presenting an introduction followed by problematic, and then the methods used in our research paper. I will be providing the results and conclusions. So as part of the introductions, we all know that breast cancer is a very harmful and a major global health issue that is particularly affecting women, and early detection is very important and crucial for improved patients' outcomes. Breast ultrasound imaging, and BUS for short, and this BUS has emerged as a cost-effective method for detecting breast tumors without harmful side effects. And we have to perform an accurate image segmentation for reliable BOS diagnosis and treatment planning. So in order to help radiologists to perform this accurate image segmentation, we are going to develop automated systems to aid in order to process the huge amounts of breast ultrasound imaging in hospitals, and we can achieve this goal by using deep learning methods such as CNNs, which have shown promise in medical image segmentation particularly, and in computer vision tasks in general. As we can see here in figure 1, we have an example of a BOS image with its respective masks. So in our work, we are going to use a dataset which comprises of BOS images with their respective masks. For the problematic, we have two limitations. We have two problems, which are that CNNs, or convolutional neural networks, have limitations in terms of capturing global dependencies, as we know that in CNNs we perform the convolutional operations, and to perform this convolution operation we are going to use a kernel size, a fixed kernel with a fixed size, for example 3 by 3 or 1 by 1 or 5 by 5, and we are going to extract features in that regions, and by doing this operation we don't extract the features or the connection, the dependencies between all the regions of the image because of this limited receptive field. And this problem, this limitation of capturing global dependencies within BOS images leads to compromising segmentation accuracy. Another problem is that with transformers that are known for capturing long-range dependencies have been underutilized in computer vision due to their problem with high computational cost. So the problem here is that we have two different type of architectures, CNNs and transformers. They both excels in certain areas, as we see here. And then the problem addressed in our research paper is how to overcome the limitations of both the CNNs and transformers individually, and we develop an efficient and accurate segmentation method for BOS images. So the idea here is that we are going to leverage both strengths of CNN and swing transformers, introducing these two architectures in a single one using a hybrid encoder, which consists of two encoders, dual encoders, an encoder that is based on CNNs and another one that is based on swing transformer. The first encoder is going to give us capture the local dependencies, and then we are going to use the second encoder, which is based on the swing transformer, so that we can model the long range dependencies that CNNs have limitations in capturing those type of dependencies. And then we are going to resolve the problem of high computational costs of using transformers by using swing transformers, swing this architecture that is going to enhance the segmentation performance and contribute to improved diagnostic outcomes for breast cancer patients. Now we are going to go to present the methods. As we can see here that our architecture is a U-shaped architecture that consists of an encoder, a decoder. The encoder part has two encoders, a dual encoder architecture, which the first one is based on CNNs, convolutional neural networks, and the second one is based on swing transformer. As we can see here that the input image goes through the first encoder. Simultaneously, it goes through the second encoder. The second encoder is based on swing transformer architectures, which I will be give details about this architectures in later slides. So as we can see here in the first encoder, we have several blocks. So each block of the CNN, it comprises a conv2d layer, a batch normalization layer, and a leaky ReLU activation function, which are performed twice, repeated twice in each block. Followed by each block, we have a downsampling max pooling DD to perform the downsampling operation, so that we are going to downsample the spatial information of the image and increases the number of channels, so that we have 5 blocks of the first encoder, and with varying numbers of filters, which with the first block, this block here, have the 64 filters, followed by 128, 256, and here we have 512 filters, and the convolution here have 124 filters respectively, so that we are going to reduce the spatial dimension, and then we are going to augment the channel dimension, the number of channels, so that after we extract the feature maps simultaneously for using the first encoder and the second encoder, we are going to have a feature map. So these feature maps are then passed through the ECA module, and ECA stands for efficient channel attention. That incorporates an attention mechanism that allows the network to selectively focus on informative channels while suppressing irrelevant or noisy information. I will be giving more details about this module in a later slide. So that after we pass the feature maps through the ECA module, we are going to concatenate them, so that we are going to form one feature map that has a rich or more representative feature maps from both the encoders. So that after we have our bottleneck layer here, what we are going to do is that we are going to use a decoder to construct the final output of our architecture, which is the segmentation mask, and we are going to use the same blocks of the encoder, but this time we're going to have the upsampling operation rather than the downsampling operation, so that we are going to reconstruct the segmentation mask. Of course, we are going to use the skip connection from the first encoder, because when we perform the downsampling, we lose important information. And then when we reconstruct the segmentation mask, we need those information, so that we get them from using the skip connections from the first encoder. And this is overall, this is our the global architecture of the proposed method. Here we are in figure 3. Here we see an overview of the ECA method, efficient channel attention module, and here as we said that we have an input tensor or a feature map. As we can see from here, we have an input feature map. The first step is to perform a global average pooling on the input feature map. This operation reduces the spatial dimensions, so that we can have only a tensor with shape 1 by 1 by number of channels. This is a single to a single value for each channel. So this operation is going to result in a channel-wise feature descriptor. It only contains information about the channels. All right, so that after we perform the global average pooling, we are going to perform a linear transformation so that to the channel-wise feature descriptor. So in order, this transformation consists of a one-by-one convolutional layer, and these layers are responsible for reducing the dimensionality of the feature descriptor and capturing channel dependencies. So by performing this one-by-one convolutional layer, we are going to capture important channel dependencies in our input feature maps. So after that, we are going to pass the resulting feature map into a sigmoid activation function. This sigmoid activation function squashes the values between 0 and 1, representing the attention weights for each channel, and these weights indicate the importance of each channel in capturing relevant information. And the last step is we are going to multiply each channel by its corresponding attention weight, which amplifies the informative channels while suppressing less relevant ones. Now we are going to give an overview of the swing transformer architectures, as we can see in figure 4 here. And as we can see here, the image, the dimensions of the image gets reduced, the spatial dimension gets reduced, but the number of channels gets multiplied, and the image goes through several stages. We have 4 stages. For the base version, we have the first stage, the second stage, and the fourth stage are repeated twice, and for this the third stage is repeated 6 times. We used the pre-trained base version of swing transformer in our work. So after the vision transformers was introduced in computer vision in the work of vision transformer in 2020, the main limitation of vision transformers is that they have a quadratic complexity, and which requires a very big resources. So Leo et al. In 2021 introduced swing transformer architecture with the main innovation, or with the main contribution is that they have the swing transformer block rather than vanilla transformer. And here in the left part we have the swing transformer block. We can see that the multi-head self-attention in the vanilla vision transformer is replaced by 2 elements, or by 2 types of multi-head self-attention, which are window-based multi-head self-attention and swing or shifted window multi-head self-attention. And this was an overview of the swing transformer architectures. So now let's move to the implementation details of our proposed method. And in our study we conducted experiments using a 5-fold cross-validation. We used 80% for training, and then 20% for testing, and the 20% of the training data we used it for validation. And of course all images were resized to 2024 by 2024, 224 pixels. That dimension is the requirements of swing transformers, because we used the pre-trained version. And our approach utilized 2 encoders, a CNN based encoder with 5 blocks and the swing transformer based encoder. We explored different combinations of batch sizes, learning rates, and epochs, with the best results achieved using the Adam optimizer. The model was trained for 200 epochs with a batch size of 8 and early stopping enabled. Data augmentation techniques were applied to the training set to enhance the model robustness. As for the results, we can see here in table 1 we have the segmentation results reported by our proposed method when it's trained on the Boozy dataset, the first dataset. As we can see here, we performed the 5-fold cross-validation, and for the mean we have an 80.5% in terms of dice coefficient, and we have a 68.3% in terms of intersection over union coefficient. In table 2 we have a segmentation results when reported by the proposed model but this time without the SCA model. So this experiment was done to highlight the importance or the role of the SCA model. As we can see here, that the accuracy or the dice coefficient was dropped slightly from 80.5 to 80.18% in terms of dice. So this highlights the importance of the SCA model. In table 3, here we have the segmentation results reported by the proposed model when it's trained on Boozy and tested on the second dataset, which is UDIT dataset. As we can see here that we have a slightly acceptable segmentation performance with a 76.44% in terms of dice coefficient and a 63.12% in terms of intersection over union coefficient, and this result highlights the capabilities of generalization of our method, since we didn't train on the second, or we only trained on the first dataset and tested on the second dataset. So in table 4 here we have a segmentation results comparison between our proposed method when it's trained and tested on the first dataset against the networks or the architectures provided in the work of Poda et al. In their work introduced in 2022. As we can see here that in terms of dice we have 80.5% in comparison to 78, 75, 76%. As well as for all the other metrics, except for the intersection over union coefficient. These results highlights that our proposed method is robust and gives slightly better performance than the state-of-the-art methods already exist in the literature. As for the visualization of the segmentation results, we have in figure 4 examples of predicted masks. So as we can see here, we have the Boozy dataset in the first half, and the second half we have the second dataset, and in the first 4 rows we have the benign tumors, and in the last 4 rows we have malignant tumors. As we can see here that when it's trained and tested on Boozy dataset, we have acceptable and perfect great results. So we can see here we have in terms of small tumors, as we can see here, we have good acceptable results. But when it comes to hidden lesions, for example in here, we have a slightly worse segmentation results due to the fact that these this example have a hidden lesion, for example here as well, but it is slightly worse. Generally, when it comes to benign and malignant tumors, there is a difficulty in segmenting the malignant type because it represents a big lesions with irregular shapes. As we can see here that the shape is irregular, so that it presents harder examples to segment. But we can see here that our proposed method gave acceptable segmentation results. For conclusions, I would say that accurate image segmentation is crucial for reliable breast ultrasound imaging diagnosis. If you propose a hybrid CNN swing transformer architectures, you could combine local and global information, which leads to improving the BUAS image segmentation. These are the references we used in our presentation and our work, and thank you for your listening and time.